So the write-ahead log in your database is absolutely critical for making sure that write performance is really fast, even in the case of lots of I/O operations happening on your database. So let's talk about how it works and how it helps the performance of your database. What we have is kind of this pre-made example here, right? We've got a couple of nodes of internal nodes of a B tree, and what we can see is the leaf nodes, this is like a B plus tree, have all of our data sitting on it, right? So this is like a really simple table where every row in the table has a ID, a name, and then an email address. And this is a kind of a very compact B plus tree where each node only has 2 rows, right? So we can fit this on the screen nicely. When you think about how a write actually works, like let's say I want to go and I want to update the Don's email address to something else. So if I'm going to go do that update, I'm going to start here and I'm going to read this node and I'm going to figure out I have to go traverse down this middle node. And let's say I'm looking up Don by ID, right? So select star from users, or I guess it would be update in user where ID equals 38, set email to something new. So we traverse the tree to figure out where this is. I go down this path, I go down this path, and then I eventually read this page in from memory, in from disk and put it into memory, right? So now I want to make this change and I have to go change this email address. So let's say it's d2@l.e, and I'm going to just make this red to kind of indicate now this page is what we would call dirty. If we, every single time a update was made or an insert was made to a table, if we always immediately wrote that out to whatever the on-disk data structure is, it wouldn't be that bad if it was just a single B tree, but a part of the problem is when you say insert a new row or update a row that has multiple indexes on it, it's actually not just one B tree update. You might have to go update several different B trees, which means writing several different random IOs to different places on your disk in order to make sure all of the indexes are in sync and the actual data row is in sync on your database. So if I wanted to insert this row, I would start here. I would find that I needed to go traverse down this way. So I'll make that green. And then I would find, hey, this is my insertion candidate for that new value. So then I would find the empty space here and I would put that in. And again, I would have to write that to disk and I would have to update all of the things that refer to that, right? All of the indexes and stuff. So we don't want to have to do that. We want our writes, when we're inserting rows to a database, updating rows in a database, deleting rows, we want those to go as fast as possible. And if I have to wait on multiple different writes to go to databases for every single one of those things before I can send back to my app server, hey, I saved your data, things are good to go. Go return back to the user, update the UI, whatever. That would make things really slow relative to the actual performance that we get out of databases. So what we would do to make this faster is we have this special structure, could almost call it a data structure, but it's basically just a log. It's a sequence of events that's happening, but a sequential file that logs every modification made to every row and every table in the database. So the write-ahead log, here's what would happen. I'm going to take all this stuff out completely. So we'll go back to the example where I was doing this insertion right here, right? So we came into the tree, had to traverse down here, had to go down here, and then I finally did the insertion over here. What we would do if we have a database that was using a binary log or write-ahead log is in memory, right? All of these pages, whenever you're doing something, updating something, inserting something, searching something in a database, you would first load that into your in-memory buffer. All these pages that are in green would be in that buffer, and I would do this insertion, I would make this update in memory, but I would not actually write this to be mirrored down in the B tree immediately on disk. So this would be what we'd call a dirty page, and in the cache, we would mark it as a dirty page. And again, this could require inserting here. There might be 10 other indexes on this table that are indexing on email and on name and on other columns. So I'd have to go make all of those updates as well. And I don't write them to disk right away. I just say update them in memory, mark them as dirty. And then what I do is in my sequential write-ahead log, I'm going to add an entry that says I did something, I made a change, or it would have an ID. So there's usually like a sequence number. So let's say its sequence is 100. And then for the row, for the table user with ID, we inserted 79. and its values are biz and b@g.ai. So this is an entry that I've put here, and this I commit to disk. So even though I might have had to update 10 other pages to fully get this thing inserted into all of my structures, the only thing that I commit to disk before returning back to the user and saying, I'm committing, I've got your stuff, is this in a big sequential file. The fact that this was a sequential file and would always be appending was a lot more important back when databases were running on spinning hard drive disks, because sequential I/O was like order of magnitude, if not multiple orders of magnitude faster than random I/O. So this is a little less important in the age of solid state drives, but it still does provide a performance boost because it reduces the number of IOs we have to do right away. And then again, let's say immediately after this happened, I went down, and remember before I did that update down to the Dawn row. We discover this is the path that we have to take. We go down here, and then I made an update just to this value. So in the write-ahead log for this, again, a new entry would be added. Copy this. So the sequence number would just be 101, because this is the very next thing that happened. For the user table, ID 38. I guess this one probably should have said insert instead of update there. For ID 38, there's an update. And then the old email was, what was it? I think it was d@l.e, and that's now going to d2@l.e. So essentially we record just the mutation that happened. I don't have to make a full copy of the entire row. I just say, this is the thing that changed. Let's log that changed. And again, commit this to disk, update all of the pages in memory, and let them know, hey, we have this new thing, but we're going to mark this as dirty, and then we send back to the user. So basically what this allows us to do is, if we're just like inserting a single row or updating a single row, we can basically commit to the client that we for sure have this thing written to disk with only one I/O operation, even if there potentially are 10 different indexes to update and a whole bunch of things to do in the database. And the reason why this is nice is because we can get back and return to the client faster, basically however long the overhead of running the query takes, plus one I/O operation. The downside is that we're essentially just deferring work to later on, because we eventually need to update this value in the B tree, and I'll change this to red too to indicate these are dirty pages that need to go get written back onto disk. So I've just deferred the work so that I can get an answer back to the user quickly. Likely when this is going to happen is if my buffer cache is full, and let's say I have this in my buffer cache and I eventually need to use this spot in my cache for something else because it's full. I need to evict something. We might decide when this is evicted, if you notice that one of the pages you're evicting is dirty, that means you actually have to write it back to disk before you can evict it. And if it's clean, in other words, it hasn't been changed since loaded into disk, then you can just get rid of it and replace it with something else right away. So when we come to this part, I would have to first write it to disk, and this could be a second later, this could be a minute later, this could be an hour later. Hopefully there's checkpointing that doesn't let it go too long, but it could be a while later that I actually finally write that out to disk and commit it. And then again, maybe this one gets written out to disk. And now finally everything on disk is in sync. If we have this sequential file, this write-ahead log, and we add an entry to it every single time there's an insertion, an update, a delete on every single table in our database, this file would just grow infinitely, right? It would just take up fill our disk on our database. It would keep growing infinitely. And so we don't want that to happen. Typically, the wall or the bin log has some fixed size to work in. And what we do is we can clean it up, or we can even treat this as like a cyclical buffer kind of thing, where we can do checkpoints. So every once in a while, if we have a checkpoint where we go through and we know, hey, like I've committed all of this older stuff to disk, like let's say I committed this one. Now I know this is for sure on disk and all of the associated pages are updated in the structure. So I no longer have to keep this in my log of changes. Because really what this log of changes is about is, if you think about like during normal operations this is running, if my server suddenly crashed and these were dirty pages, those are not going to be on disk, right? And so then when the server starts back up, I would use these to recover and get my database back into the correct state. But once I know it's committed to disk and like this is green, then I can get rid of this segment right here. And then I can then reuse that space in the write-ahead log for something else. Once I've committed this to disk, I no longer need this in there, and I can reuse that space for something else. So this is basically why we need the write-ahead log, right? We want to be able to, one, commit back to users quickly that we've received their query and that we have their data safe and secure on disk. And we want to have a mechanism to recover from crashes for that, because we can't just rely on, hey, we have your thing in memory, because if I say I've saved your thing and it's not actually on disk and then the server crashes, I'll have forgotten something that I told you I committed as the database. So that's how write-ahead logging and binary logging works in databases like MySQL and Postgres. There's a lot more cool, interesting details about the specifics of what goes into those write-ahead logs, the formatting of those, and how the data structures are updated, and when we flush those pages to disk. That will be for another time, but hopefully this helps you understand how we can respond to clients quickly when committing data to disk.